This video is about chi-squared tests. We have two different chi-squared tests. One is a test for independence, and one is a test for goodness of fit. So I'll first go over the chi-squared test for independence. If you recall, we, in Chapter 5, discussed the dependence or independence of two variables. This is very similar, but we can actually do it for categorical variables. And we actually we started out in a similar way with the contingency table, kind of like we had before. And we can also end up with a p-value, so we start out with a null and an alternate hypothesis, and then just like all our other hypothesis testing, if the p is low enough, we can reject the null and go with our claim, or the alternate hypothesis. So we start out with the null hypothesis that the two variables are independent, and the alternate hypothesis that they're dependent, or basically there is some sort of correlation. Okay, so let's say that I wanted to test whether or not gender and accounting major were dependent or independent. So basically I'm wanting to know if someone's male, are they more likely to be an accounting major or less likely to be an accounting major? And I have this information about how many males are accounting majors, how many males are not accounting majors, how many females are accounting majors, and how many females are not accounting majors. That's really all the information I need. I don't need these totals here. But if you remember from before, that can come in handy if you're looking for probabilities. Okay, so chi-square test for independence, I'm going to go to add-ins, megastat, chi-squared / crosstab. We're not going to do cross-tabulation in this summer session. We never cover that anyway. So we're just going to do chi-square test using a contingency table. And then, as I mentioned before, our second topic will be chi-squared test for goodness of fit. Right now I have 3 examples of the contingency table chi-squared test for independence. Okay, so if I just click contingency table, it's just basically looking for me to select a contingency table. Okay, so all I have to do is click on those main values in my contingency table. I don't have to include the totals or the labels. I could include the labels if I wanted to. Okay, and chi-squared is already checked. Click on OK. And basically, chi-squared is like a test statistic. Just like the z-score was a test statistic, the t-value was a test statistic, and based on that test statistic, we get a p-value. The p-value tells us whether we can reject the null or not. Okay, so in this case, our p-value is quite low. It's below the 3 common levels of significance of 0.05, 0.1, and 0.01. So because of that low p-value, I can actually reject the null, okay, that they're independent, and actually go with the fact that they're dependent on each other. So basically I'm saying whether or not someone's male or female will basically kind of predict whether they're going to be more likely to be an accounting major as well, just like we had before for dependent and independent variables. Okay, just using another example, let's say we want to know if the fact that someone smokes is dependent on their race. Okay, so I have these numbers here: 145 white people that smoke, 15 black people that smoke, 60 black people that don't smoke, and 280 white people that don't smoke. Okay, if I go to add-ins, megastat, chi-squared test, using the contingency table, just clear. Okay, just select that contingency table. Chi-squared is already selected. This time, your chi-squared, or test statistic, is 5.84, and your p-value associated with that is 0.0157. So, in this case, if we had a level of significance of 0.05, our p-value is less than 0.05, so we could reject the null and go with the fact that they are correlated. However, if I wanted to be a bit more strict and I had a level of significance of 0.01, I could not reject the null, so I'd have to go with the fact that they're independent. In other words, I have no proof that there's some sort of correlation between smoking and race. Okay, going back to our data, here's a good example from the book. Let's say, after JFK crashed his plane, they actually wanted to find out if people thought that non-instrument rated pilots should be able to fly at night. The thing is, they asked people that were experienced pilots as well as just the general public, and they wanted to see basically does their answer, yes or no, depend on whether they're experienced or not? Okay, so is experience dependent on their answer to that question? Okay, so they asked some experienced pilots and the general public and got 40 experienced pilots that said yes, non-instrument rated pilots should be able to fly at night, and 29 that said no. The general public, the majority said no, they shouldn't be able to fly at night, and 61 said they should. Okay. Again, our null hypothesis is that the two are independent. Basically, we're saying until we can prove otherwise, we have to assume there's no relationship. Our claim is that maybe there is some relationship. Okay. Go to Megastat, chi-squared, contingency table, clear, and I just go ahead and select my contingency table numbers and check out the chi-squared. Okay, really low p-value. And you can see a high chi-squared. Kind of like in the past, it may depend on the sample size, but generally we tend towards if there's a high test statistic, there's going to be a low p-value if we have a reasonable sample size. So our chi-squared is quite high and our p-value is quite low, meaning we can reject the null hypothesis that the two variables are not related and go with the claim, or the alternate hypothesis, that they are dependent on each other. Basically, whether someone said yes or no was dependent on the fact that they had experience or not. Experienced pilots probably have a better idea of whether or not non-instrument rated pilots should be able to fly at night or not. The general public is going to probably, be cautious and most likely just say no without knowing further information. Okay, and that is basically the chi-squared test for independence. It's very similar to the test for independence that we had before, only once again we can use it for categorical variables, and we treat it as a hypothesis testing where we can get the test statistic, or chi-squared, and a p-value associated with that. Okay, next I'm going to turn to chi-squared goodness of fit test. Okay, so the goodness of fit test is basically saying, does my data follow a certain distribution? Okay, so basically my null hypothesis is that my data does follow an expected distribution. The alternate is that it does not follow the expected distribution. Okay, so kind of like the assume innocent until proven guilty, I'm going to assume it follows a certain distribution unless I can prove otherwise. So here's a good example. Let's say this instructor is hoping to have a distribution like this: 30% A's in the class, 30% B's in the class, 20% C's, and only 1% D's and F's. Okay, that's what we can call, I guess, the expected distribution or hoped distribution. And he wants to see if there's evidence that it's against that. Okay, so he has a class of 49 students. Notice these are percentages. So to get what we should expect in a class of 49, we basically just take, as you can see in this formula up here, the percentage that we're hoping for times the number in the class, 49. Okay? And basically do that for each grade level. That should sum up to 49, the total in my class, and as we know about probabilities, these should add up to 1, which they do. Okay? So the way I'm calculating my expected values is just taking what the expected percentages are times the total in my class, and this is going to represent number of students that should get A's, number of students that should get B's, and so on. Okay. Here's what he actually observed. Okay, so when we do a chi-squared goodness of fit test, we do actually observe certain numbers and then see if those numbers follow what we're hoping or expecting. Okay, so he observed 10 A's, 20 B's, 15 C's, 2 D's, and 2 F's. Okay, again, total of 49 students. All right, once you have that information, it's really easy to go into Excel, Megastat, chi-squared, goodness of fit test, and all we have to do is select, okay, what are the values we observed, and what did we expect? Okay, make sure you're not including that total in there. Okay, Excel knows that basically you've already calculated what to expect based on a certain probability distribution. Okay, once again we have a chi-squared test statistic and we have a p-value associated with that. Now at the common level of significance of 0.05, our p-value falls lower than that, so we can say we reject the null, that it follows the expected distribution. Basically, we have evidence that it does not follow the expected distribution. So in this case, a low p-value not necessarily maybe what we want, because if we're wanting to follow this expected distribution, then we're finding evidence that we haven't actually followed that distribution. Okay? But then again, he can maybe change grades around and see if he can actually fit the expected distribution. Okay. But of course, at a different significance level, let's say we said 0.10, or I'm sorry, at 0.01, if we want it to be more strict, at 0.01, he would not reject the null, and he can say that he does follow the expected distribution. So there's again another example of where researchers, statisticians can kind of, there's some flexibility there based on the level of significance. Okay, so, but many times p-values are so low or so high that it doesn't matter what the level of significance is. But here's a good example of where it does. All right, let's give another example of that goodness of fit test. Let's say that, let's take a look at this column first. On the official M&M's website, it tells us what percentage of each color M&M should be in a given bag. Okay, so 13% should be brown, 13% should be red, 24% should be blue, and so on. All our probabilities or percentages should equal 1, which they do. Okay, and we had a bag of M&Ms that had 57, and then we had one of those mega supersized bags that had 104 M&Ms. Okay, so we're just going to do two different tests of the same thing to see if, obviously the number doesn't matter, it's more the percentages. Okay, so we observed 5 brown, 8 red, 12 blue, 13 orange, 4 green, and 15 yellow. That's what we actually observed. Okay, so we observed 57 M&Ms. What we would expect is 13% of 57, which is 7.41 for brown, 7.41 for red, 13.68 for blue, and so on. So see how the expected column comes from taking the official percentage times the number that we observed. So we have an expected that may be very different from what we actually observed. Okay. So expected is just the official percentage times the total, and we do that for each value to get the expected values, and this is actually what we observed. Okay. So go to Megastat, chi-squared test, goodness of fit test, and once again we put in our observed values and our expected values. Okay, and as you'll see in the slides, the goodness of fit test is really looking at the difference between observed and expected. Okay, so how far away is what we observed from what we expected? Obviously, if it's close to 0, then we have a good fit. Okay, so in this case, our chi-squared is 10.31. That's our test statistic. And our p-value is 0.0669. So, if we have a level of significance of 0.05, most common one chosen, we cannot reject the null. Our p-value is a little bit too high to reject the null. So, we have to go with the null that our data does follow the expected. Okay, so again, the null in this case is positive in many ways. We want to say that we're following the expected or official distribution. And in this case, we could say official, because that's what it says on the official website. So we're basically just saying, does a random bag of M&Ms follow the distribution that they say on the website? Okay. And just to show you a little bit more of what's actually going on with that, actually, we'll just go back to the data examples real quick to show you a little bit more about the chi-squared test in a contingency table. See how they have expected values and O minus E and then O minus E squared over E. That's actually doing the same thing, observed minus expected. So both chi-squared tests are really about seeing how different what you observed is from what you would expect. Okay, and for now that is it about chi-squared test for independence and chi-squared test for goodness of fit.